Here is a related rates problem that I remember doing when I was in Calc 1. And so it's probably a common example. It's probably one of the classic related rate problems that you'll see when you do these type of problems. And the idea here is you have this 13-foot ladder leading up against the house, and it begins to slip away from the house, so the ladder's falling down, sliding down the house. And we're told here that when the bottom of the ladder is 12 feet away from the house, the rate at which it's sliding away from the house is 5 feet per second. And so it's wanting to know at that point how fast is the top of the ladder sliding down the house. Okay, so what we're going to do, let's get some variables here. I'm going to call this variable x, so this side is x, and see, this actually is forming a right triangle, right? This side is x, and this side will be y. And so then what I can do is I can write the rate of change that it's sliding away from the house as dx dt, right? And I'm told that that's 5 feet per second. 5 feet per second when x is 12 feet away from the house. And notice that's a positive 5 feet. Why is it positive? Well, because x is increasing. As this ladder slides down, this length is getting bigger, right? The y here is decreasing, though. Y is the height of the ladder. So this rate, when we're done, this rate better be negative. Okay, so, and that's what it wants us to find. It wants us to find dy dt at this time, right? At this time. Okay, so if this is the rate that it's sliding away from the house, then what is the rate that it's sliding down the house? Okay, that's the idea. Okay, well, notice in this problem, unlike the ones we've done so far, we are not given any sort of equation to take the derivative of, right? We're going to have to find the equation. So we need something that relates these things together. So do you know anything that relates the x and the y with the length of the ladder? I bet you do. It would be the Pythagorean Theorem, right? This is a right triangle. And so the equation we're going to use is just the x squared plus y squared is equal to 13 squared, right? That's what relates these two, the x and the y, together. Okay, so we're going to take the derivative of this, take the derivative of both sides with respect to t. And so the derivative of this with respect to t. Right? Well, when you do this, this here, using implicit differentiation, is going to be 2x dx dt plus 2y dy dt. Okay? And then this is just a constant. So with respect to t, taking the derivative of a constant is just 0. And now I want to find the dy dt, so I'm going to solve for the dy dt. So this would be dy dt. I'm moving this to the other side, 2x dx dt. But then I'm dividing all that by the 2y, right? It would look like that, but this will simplify here to just negative x over y dx dt. That's how that will simplify. So notice when x is 12, dx dt is 5 feet per second. So I do need to know the y, right? But we can find that with this right triangle. So this is 13, this is 12, and we want to find the y. So that's just a simple Pythagorean Theorem problem, right? 12, 13, and that's y. So you have 12 squared plus y squared is equal to 13 squared. Okay, so y squared is equal to, that'll be 169 minus 144. And so I get y squared is equal to 25. And you know it's a textbook example when this comes out even. You take the square root and it comes out evenly, right? So y is equal to 5. And so now I can find the rate that I want. dy dt is equal to, this will be a negative, and then the x is 12, the y is equal to 5, and the dx dt is equal to also 5, right? Like that. And so it looks like these cancel out, and I just have negative 12 feet per second. So the rate at which it's sliding down is 12 feet per second. Okay? There you go. Very nice related rates problem. And then the follow-up to this problem that you will often see is something like this. So in this case, it's the exact same situation, a 13-foot ladder sliding away from the house. But what I want to find now is I want to find the rate of change at which the angle that the ladder makes with the ground. What's the rate of change of that with respect to time at the same time when this is 12 feet? Okay, well, this is going to involve another relationship, and it's going to be a trigonometric relationship. You could probably guess that. And this is x here, and so I think we're going to use cosine, right? Because I have x, and I know the rate of change of that, right? So dx dt is 5 feet per second when x is equal to 12. And so I'm going to use that the cosine of theta is equal to x adjacent over hypotenuse, so x over 13. So this is a relationship that relates the x together with the theta, right? We're relating the theta, the angle, with this x. And so now I can take the derivative of both sides of this. So with respect to t, and when I do that, this is going to be, when I do this implicit differentiation, treating theta as a implicit function of t, I'm going to get the opposite of sine of theta times d theta dt. That's what this will equal. And so this one will just be 1 over 13 dx dt. Okay, and I want to find d theta dt when x is equal to 12, it looks like. And so I'm going to bring this down, so this will be d theta dt is equal to, and I'll get 1 over 13 dx dt all over the opposite of the sine of theta. Now the thing is, I need to know what the sine of theta is. So a couple things. I suppose you could find theta at that moment, right? You could put 12 here and find what the theta would be for cosine theta. But probably the better thing to do is just use the right triangle trig here. This is 13. When this is 12, we found before that this side was equal to 5. And so for that angle then, the sine of theta would just be 5 over 13, the opposite over the hypotenuse. So for this, I would just use that. And so we can plug these things in. 1 over 13 dx dt would be the 5. And then all of that is going to be the opposite of the sine of theta, which is 5 over 13. Right? And so I could invert and multiply. So this would be 5 over 13 times a negative 13 over 5. And all of this is negative 1. And what's the units on this? Well, since we use the derivative rules for sine and cosine, theta has to be in radians. So negative 1 radians per second. So this angle is getting smaller, and in this case it would be, at that moment, it would be changing at a -1 radians per second. Okay, so there you go. That's the classic sliding ladder problem, I guess, and you can find the rate of change of one side when you know the rate of change of the other. You could also find the rate of change of the angle that the ladder makes with the ground.